Okay. Let's do this one more time. This is gonna be like the seventh time I'm doing this. Hopefully I get it right. Let me start by sharing my screen very quickly. You choose the screen to share. And while that is being done, my name is Renee, and I want to be talking about the traveling salesman problem. I am a student at NC State, and this is an interesting thing that I want to talk about. So my conversation today is based off an article that was written in 2020 um, by was written in 2020 by Rene van Bevern and Slogina. These were probably Soviet mathematicians. And so the traveling salesman problem, and what is this? So imagine that you have somebody who is selling something like, we'll say he's selling newspapers, just to keep it simple. And he has to sell newspapers across the entire state. Every state is made up of cities. And so he has to go through every city selling his newspapers. He starts at a particular city and he is required to go through every city and return back to the city where he started. And he does not have to go through any city twice, so at most one time. And he also has to find the shortest possible route to take. Now, that may seem easy for a small number of cities, but you can show very easily that once the number of cities become larger, the solution to this problem becomes what is called an NP-hard problem. It becomes extremely difficult, and there is no algorithm that exists that can solve this problem in polynomial time. Okay, so what are the steps of the algorithm? The first thing is that we begin with a weighted complete undirected graph. And this graph is like our state. And the vertices of the graph are the cities. The edges in the graph are the roads that connect the cities that the salesman has to go through. Okay, so we start with that graph. It's a complete graph, meaning that every vertex is connected to every other vertex through one edge. It is connected, meaning, of course, you can begin at every vertex, you can touch every other vertex. All right, so the next thing that we do is we find a minimal spanning tree. From this, we use an algorithm called Christofides algorithm. Christofides algorithm, sorry, to find a minimal spanning tree. And basically, what we are trying to do here is that there is a distance associated to every edge. That is called the cost. And when we find a minimal spanning tree, it's basically a subgraph that has all the vertices of our original graph, but the edges are such that when you add up all the cost on those edges, you get the smallest possible number. So that one, so you can have many spanning trees, but the one whose total cost is smallest is called the minimal spanning tree. So we get that. In our minimal spanning tree, some edges, sorry, I was going ahead of myself here. Print the slide. So I'm going to put it on this is the most important part of the slide right here. So the process that I'm describing is called the Christofides algorithm to find what we'll discover is, we'll come to term it as the Hamiltonian Tor. So after you found your minimal spanning tree, some of the vertices will have odd degrees, some will have even degrees. You cannot find a Eulerian circuit if the vertices exist with odd degrees. So you have to find some kind of way to make all those vertices to have even degrees. So what we do is we take every odd degree vertex and we pair it with another odd degree vertex. So we are basically drawing an edge there, adding an edge. So we pair them together, and the edge that we also add is based on the shortest possible path. Okay. Now, I left out something, but I'll mention that again later. I said that this solution was NP hard, but it can be reduced to a very good approximation if we make some two assumptions. The first assumption is the assumption of the triangle inequality. Basically, we call that as those assumptions symmetry as no, sorry, we call them metric assumptions. So we know the properties of the metric is that one, there's this triangle inequality that should hold, and there's also symmetry that should hold, meaning that the distance between any two cities, the distance between city A and city B is the same as the distance between city B and city A. That's called the symmetric property of the metric. And the triangle inequality property is that if you have three cities, city A, B, and C would be in the middle, the distance between the first city A and B, the distance between A and C should be less than or equal to the distance between A and B plus the distance between B and C. That's called the triangle inequality property. So with these metric assumptions in place, we have what is called the metric traveling salesman problem. Okay, we were at the point where we had our metric. We had done our pairings. We now take the set of these edges that we have paired. It forms a subgraph of its own. We unite this with the minimal spanning tree, and that gives us a multi-graph. And this multi-graph will have only even degrees. And by Euler's theorem, a Eulerian circuit, will exist for this arrangement. And therefore we can find that Eulerian circuit using Flory's algorithm. Okay, now how do we get our Hamiltonian Tor, which is really what we are trying to get at? That should be the output, like we see here. The output has to be a Hamiltonian Tor. While we are traversing the Eulerian circuit, whenever we encounter an edge that we had met before, we delete, sorry, not an edge. Whenever we encounter a vertex that we had met before, we delete the edge that connects the current vertex to that new vertex that we were supposed to meet. We delete that edge, and then we draw another edge from the current vertex to the next vertex that we're supposed to visit. So this process is called shortcutting, and it's very, very important. So after we've repeated this and gone through all the vertices and come back to where we started, the path that we would have mapped or carved out is called the Hamiltonian Tor. And Christofides algorithm is guaranteeing that the total distance of this Hamiltonian Tor is less than or equals to 1.5 times the total possible distance that we could have, in the most efficient graph. So that is really the core. Now going to the 3/2 approximation is the part. So 3/2 is the same as 1 plus half. The part of the 1 is fairly easy because you delete an edge from the minimal spanning tree, the cost reduces, but so it reduces and becomes less than what the optimal cost could be. Now the 3/2 comes from the fact that we will be skipping every other odd degree vertex. So we'll be, as we are traversing our Eulerian circuit, we'll skip every other odd degree vertex. So at the end would have gone only through half of them. When we add the total cost, we'll have exactly half what the optimal cost could be. So when you add this half plus the 1, you get 3/2. That's the most straightforward explanation using the shortest possible time. I'm going to end my video here. I don't want to take much time. If not, it's not going to record. Thank you so much for your attention, and this brings me to the end of my video.